Good afternoon to everyone. Today I will present the development of a portable device for manganese detection in water using colorimetric principles. My name is Gonzalo Ezequiel Alemani Duarte, and the contributors to this work were the doctors Arturo Hernández Hernández, Pablo Antonio López Pérez, Luis Alberto Hernández Hernández, and José Alfredo Pescado Rojas. As an introduction, manganese contamination in water sources, especially in Hidalgo, poses several health risks. Prolonged exposure can cause neurological disorders like manganism, that which can resemble the Parkinson disease. Shockingly, wells in Santa Cruz and Chimalpa, regions of Hidalgo, contain up to 4.05 milligrams per liter and 3.718 milligrams per liter respectively. This is far exceeding the Mexico safety limit of 0.15 milligrams per liter dictated by the norm 127 SSA1 2021. For portable device detects manganese by measuring permanganate absorption at 525 nanometers using the Beer-Lambert principle. Designated for remote field use, it combines the EPA standard method 3500 mmB pretreatment with a low-cost optical system that we developed. This enables rapid on-site water testing by trained personnel, eliminating expensive lab equipment. Our goals for the development of this device was to create a device that can differentiate manganese concentrations via colorimetry and evaluate an adapted persulfate pretreatment based on the standard method 3500 mmB to oxidize manganese to permanganate. Continuing to the methodology, the first methodology followed was the persulfate method, in which we needed a special reagent that consists of sulfuric acid, nitric acid, silver nitrate, and distilled water. The next step was the preparation of 0.1 normal potassium permanganate solution, and we standardized it. Next, we prepared a solution of oxalic acid and a solution of sulfuric acid 1 plus 1. This was needed to prepare an Mn stock solution by reducing the MnO4 to Mn2 plus. Next, we prepare with this stock solution a 50 ppm solution that we then diluted to 10 ppm. The next thing was to dilute this 10 ppm solution to 2.5 ppm solution. We transferred then 25 milliliters of this to a 100 milliliter beaker. We added the special reagent to the solution, and then we add a drop of 30% hydrogen peroxide. We added 16 milliliters of distilled water and 1 gram of ammonium persulfate. Then we boiled for 1 minute and we waited. The results wasn't what we expected. There wasn't a noticeable color change, and we observed a formation of white precipitates at the bottom. This was probably due to the presence of chlorides in the solution. Because we didn't include mercury sulfide, it caused that the reaction wasn't completed. The second methodology followed was the design of a photodiode and a LED array that in between them will be a glass container that we will put the samples there. Then we write a code in Arduino and we simulated in Tinkercad. We then assemble this circuit in a protoboard. For the principal components were a photodiode that was the BPW34, an operational amplifier that was the LM358N, and a green LED. We cut then the pieces of the optical array into cardboard. We painted them black. Then we assembled these with the electrical components. We mount them in a cardboard box, and we prepare different MNO solutions. Then we measure the voltage produced by the different solutions with the photodiode. We created a calibration curve by a linear fitting, and we determined then the linear equation. And finally, we tested with different MnO4 samples at varying concentrations. Passing to the results, here is the sensor circuit design, and is simple and reproducible with off-the-shelf parts. Here we had different MnO4 dilutions ranging from 0.1 to 50 ppm. Here is the device functioning. We can see in the left the interior of the device, and in the right we can see the LCD displaying the results of the samples. Finally, the sensor achieves a manganese detection from 0.1 ppm with 0.5 ppm resolution, providing compliance monitoring capability against Mexico's 0.15 ppm water quality standard. In the first image, we can see the calibration curve, which the points were 0.1, 0.5, then 1 ppm, 2 ppm, 3 ppm, 4 ppm, and finally 5 ppm. The next image shows three measurements made, and we can see that the absolute error doesn't vary too much. It is close to 3.5 ppm, and this gives good estimation for field use. The last graph was of the same three measurements and gives precision or repeatability error bars. On average, the standard deviation is 0.01389, and this is mostly limited by electrical noise. The next thing is a video sample of the device while testing a standard solution or 4 ppm. We can see that it gives that the manganese present is 4.119, giving a good estimation from that we can use to obtain preliminary results. And finally, for the conclusions, we can see that this device works with simple chemistry. It uses this persulfate method to turn manganese 2 plus into purple MnO4, and it measures the absorption with a green LED and a photodiode. This device is cheap because it's made with low cost parts like the operational amplifier LM358N and a basic LED. Is accurate enough for field testing, is easy to improve later. We can use better operational amplifiers like the OPA 381, that is a very op amp that has a lower offset and lower noise. The next thing that we can improve is using spectral image LEDs with narrow emission at 525 nanometers. This device is a game changer for the small communities that are remote and need a good, fast, and accessible device that can control and monitor the water in the area. And this is all for my part. Thank you very much.